Hey, good morning, everyone. Can you guys hear? And can you see the screen?
Yes, sir.
All right, so today we're going to start off with inclined planes. If there's anything specific about them that you want me to go over, maybe offer some insight, you can tell me and I'll see how I can best explain that part. Now let's just start talking about inclined planes and how we should approach this question. So let's start on flat ground. Yeah. It's fairly horizontal. And let's say we had an object, maybe preferably a round one. Right? Might be better to visualize. Okay. So now this round object, let's say a barrel or a box, some load, would have some forces, right? As we would expect. These forces include weight, which is as a result of gravity, right? Now, these forces can, of course, be broken up into its orthogonal components. And if we were to say vertical and horizontal component, we'd notice that this force has no horizontal component. It's purely vertical. And that's because this ground is flat. Now, if we were to rotate this up a little bit, like this, what would happen to this barrel? It would roll down this way, wouldn't it? Roll down this way. And that's because we now start to introduce a component into our weight. Right? So weight still acts vertically downwards. But now, it's made up of two orthogonal components, as always. One that's perpendicular to this slope, and one that's parallel to the slope, right? So we find that this is the force that makes the barrel want to roll down. Yeah. Now, to oppose that, we would need something holding it back up this way, something pulling it back this way. I should oppose this force. And this force is being counterbalanced by the reaction of this inclined plane or this slope. So we'd have something come up in the same general direction as this. And right. Okay, so this same general direction. Okay. These are the mechanics of an inclined plane. Now, alternatively, let's say we had enough friction, this thing was sufficiently rough, or a round object isn't the best way to display this, but let's consider that this was square with a lot of surface area, right? A lot of surface on surface contact. Then we could say that friction could be able to hold this back up, right? So the weight would be acting down. Yeah, it would have this component here parallel to the plane. This one here, would be counterbalanced by the plane, and we would say if there's enough friction, then friction could possibly hold us back up, and the system would still be in equilibrium. Right? Now, why would we want to use an inclined plane? Well, as opposed to when the system was flat, right? In order to move this object up, let's say it's a 2-meter point, yeah, or some height, what we'd have to do is lift this object straight up, right? lift it up. And here we'd be directly opposing the force. So let's say we take it straight up, the path 0 to 2 meters, right? We'd have to oppose this force W. So the work done here would be W times 2, right? Where W is the weight of this thing. So to move it like that, right, we'd have to do W times 2. Now, with an inclined plane, with this inclined plane, we noticed that we wouldn't have to oppose the full magnitude of the weight, right? What we have to oppose is this small component that is parallel to the slope, yeah? So you'd have to oppose this if you wanted to move it up. So based on this gradient, right? Of course, we'd have to move some longer distance to get some shorter height based on this slope, right? Some longer distance L based on this height, right? But we'd still achieve the final outcome, we'd still achieve that same height. So as you'll see, and I'll just put this formula down here, WH, the work done on this load to raise it to that height, would be equal to the force we use, this force here, F, push it up, times the length traveled. Now, because L is bigger, we find that the force we need to push this object, the initial force, right, would be smaller than W, right? S is less than W. It's just that we have to push it for a longer distance. So it's like spreading the work out. We're still accomplishing the same work, right? Still doing the same thing, but we're stretching it out and we're using a smaller force because sometimes some people might not be strong enough to lift this barrel straight up, or your forklift might not be strong enough to just carry a barrel up, or whatever it is, right? So what we do is we use a smaller initial force, right? And we can see that from this diagram here. Most of the component of the weight is being counteracted, is being supported, equally opposed by the slope. And just this small piece here is what we're pushing against, right? Now, if this were to, of course, move here, what we would find is this here would get longer. Let's call this B. B would get longer, would approach the weight, right? Would start to approach the weight. And this here, C, would shrink, and then with C would start to become zero, right? Would approach the weight. Just general idea of an incline plane. So let's just start off by working number one, and we'll prove the formulas as we go about. Body having a weight of 500 newtons is placed on a smooth inclined plane, 5 meters long. The top of the plane is 2 meters above the lower end, right? Calculate the force required to hold the body in equilibrium if it is applied A, parallel to the plane, or B, horizontally. So let's set up our inclined plane. We know the inclined plane is 5 meters long, and we know it's smooth, right? So 5 meters long and smooth, this reaction force, this reaction counter force here from the contact force here, and it's smooth, so no friction, here must be 90 degrees, right, to the plane, to this plane here. Yeah, agreed? Now, we're holding the body in equilibrium, right, keeping it from falling down. That's called our force F, and we're applying F two ways. One way, parallel to the plane, and secondly, horizontally, right? Horizontally would be this way, right? Applying F this way, as opposed to here, parallel to the plane. So let's start off with parallel to the plane. And of course, as I said, 5 meters long and 2 meters high. 2 meters above the lower end or above ground, right? So this here should give us a sense of how steep this inclined plane is. And from that, we can go about deducing all sorts of angles. So here, we notice something. We notice the body has a weight of 500 newtons, and that, of course, acts vertically downward, right? 500 newtons. So nothing new, nothing unusual about this setup. So let's try and analyze it with things we already know. So something we already know, three forces in equilibrium, they make a triangle. So let's try and make a triangle. This here is parallel to the plane, and this is perpendicular to the plane. So this here should be a right angle, shouldn't it? It should be a right angle. So let's bring that out. Here we have R. Here we have F. So let's move F. Let's move F up here, right? Move F up to make the triangle, right? Let's move F up. And then let's slide W up here, right? And because the three forces, they make a triangle, W should be this vertical one here, right? And they go around cyclically like this. So again, nothing new. It shouldn't be unfamiliar to you, right? So here is the W. Here is F. And here is R, right? So let's look at the angles. Here, we know it's right angle. And even if we slide it up here, here is still going to be a right angle. Agreed? This here is also 90 degrees. Now, for this angle here, we don't know what that is, and that's based on sliding this one up here. So that should be the same as this angle here, right? Okay. So what is that? What is that angle? Let's find out. So if you would remember the ladder problem, we did a little piece of deduction, and we realized that this angle theta for a very similar system is this angle alpha is also this angle alpha. So here, if here is alpha, then here, x angles, right? Let me write this. Yep, this angle alpha is also this angle alpha, which is this angle alpha, right? So let me go over that a little bit more in detail. Okay. Let's just extend the slide now. This here would be a 90-degree angle. So this angle here should be from 90 minus alpha. Let's call this angle theta. Yep. Theta is equal to 90 minus alpha. You can see that, right? Because 180 degrees minus 90, we got 90 left. So these two should be 90, right? Subtract alpha from 90, we get theta. Okay. Now, also here, since this is parallel to this, This angle here is also theta. Yep, this angle here is also theta. Let me draw that back out. Two parallel lines like this. Here. Angle here is the same as this angle here. Yep. So this angle here is also theta. So here we have two things. We have this line parallel. This line parallel, let's draw that over here. And this R, which is perpendicular to the slope. Yeah, perpendicular to the slope. And then we have W, weight, coming down. Let's draw weight in blue. So the weight. Let's draw the weight down. Yeah. So we know here is theta. Great. All right. So what is this? Well, theta is equal to 90 minus alpha. This here, right? Parallel to the slope and perpendicular to the slope. This here should be 90, right? So 90 is equal to theta plus mystery angle, right? Mystery angle. Let's call the mystery angle C. So C should be 90 minus theta. Yeah, 90 minus theta. Now you should already start noticing that it's alpha, right? 90 minus theta. But let's keep working. And theta is equal to 90 minus alpha, right? So 90 minus theta, which is 90 minus alpha, right? Let's just remove these brackets, multiply out by the negative sign here, right? This and this subtract, so we're left with alpha. So now we know certainly that this angle here is alpha, which is this angle here. Great. Let me draw this a bit bigger, since we know that the angle is alpha now. R, F, and W. Right? So here's alpha. We concluded that this was a right angle. This is W. This is F, or force F. Right? Force F. And this is R. So calculate the force required to hold the body in equilibrium if it is applied parallel to the plane. And this is what we have here, right? Parallel to the plane, 90-degree angle. So what is F? Well, you can simply just write down F equal to W sine alpha. Does everyone agree with this? Any doubts? No? Okay, great. Just use a trig ratio. F over W is equal to sine alpha, sine the angle, right? Then just carry over the W, so you find for F, right? So F is equal to W sine K, sine alpha. So this alpha is also this alpha. Different triangles, but same alpha, same angle. And sine of that angle in this triangle is equal to here 2 over 5. 2 over 5. So for this question, we could replace that with W times 2 over 5, or generally, for all questions with a force parallel to the plane, we can say F is equal to the height, which is 2, the height over this length here, 5, right? H over L. Agreed? And from that, it's where we get the equation for work. F times L is equal to W times H. Work done on the load is equal to work done along the plane, right? And you find that this here is longer, this is shorter, but these forces, this one should be smaller, right? F is less than W. So we use less total force, less force in general to do the same thing. Okay. That's the first equation down. And I just wrote them on the top here, so you can just remember them all the time, right? So when the effort is along the inclined plane, with that same setup, right? F is equal to W sine alpha. And this, we can always break this down as F equal to W height over length. And we can carry over and do the work. 1, 2. That's the first one down. And let's work the question. A body having a weight of 500 newtons is placed on a smooth inclined plane, 5 meters long. The top of the plane is 2 meters above the lower end. Calculate the force required to hold the body in equilibrium if it is applied A, parallel to the plane, and B, horizontally. So here, parallel to the plane. We established the formula. We established that sine alpha is also 2 upon 5, right? Just a regular trig ratio. We established that. So solving for F is fairly trivial as long as we establish this formula. And this formula will apply to all of these inclined planes. So when you see a problem with the force pulling parallel to the inclined plane, just put this formula down, swap out what you need to swap out. Sometimes they give you the angle, or sometimes they give you the sides. Okay? But regardless, this will be the formula. Then you plug this into a calculator and you get 200 newtons. And that's it. That's part A of the question. Very easy. Now for part B, where the force is horizontally. Good. Let's do this thing again. W here. Push it up. We established that this here is alpha. Yeah. Right. So this here is R. Is R. This is W. This is alpha. And we're sliding this here, right? And this is the right angle. So here was the right angle. This here is horizontal and this is vertical. So here's the right angle, and we move it, like move it here and then up here. Here becomes the right angle, right? Again, let me just draw that a bit bigger. So here is W, here is F, and here is our R, and this angle, as previously deduced, is alpha. Right, good. So we end up with now an equation that says F is equal to W tan alpha. Tan alpha. So that was F, or better, tan alpha. Tan alpha is equal to opposite adjacent, right? F over W, and we solve for F, right? Easy. Good. And just like the previous question, we can substitute tan for two things. W, here is the height, over the base, whatever the length of this base is, okay? And that's tan alpha. So tan alpha is the height over the base. That's what we have here. So using that formula, we can solve this question. When the effort is horizontal, we put a formula down. We substitute tan alpha for 2 over the base. And in this question, they didn't give us the length of the base, but using Pythagoras Theorem, since this is a right angle, we can find out what B is very easily. We put a formula down, we replace the weight with 500 newtons, which was given to us in the question. And then we know our height 2, but we don't know our base. So we solve for a base using Pythagoras' theorem. Hypotenuse is 5 squared minus 2 squared plus 25 minus 4, and that's 21. 21, and the square root of 21 is 4.583. And you can double check this with your calculator. And now, having found B, we reintroduce it into our formula, input this 4.583 back into our formula, and then we solve F. Simple, easy. As long as you know this formula, you should be able to get this question done. Any questions? No? Okay, moving on. Now, there is another case that I would like to explore. So let me just explore that in Paint. So again, our inclined plane. We have some object. Resting on the inclined plane. Here is the reaction, which is perpendicular to the plane. Put these forces in, right? Here is the weight, which is vertical. And let's say we were to apply a force to hold the system up at a weird angle, some angle. Let me get my charger. Yeah. So we're putting the effort some weird angle. Some weird angle theta. Yep. and this here would be a regular alpha, right? Some weird angle theta to the plane. Yep, this is a new case. So what would be the formula for this? Well, let's construct a triangle and see. So again, we move the weights up this way, and we know here is also alpha, right? And this we move across, but the triangle is gonna look a bit different, right? It's gonna have weight down, right? It's gonna have this R here coming across here, right? Then it's gonna have this here coming at a weird angle here, right? So here is not gonna be 90, not 90, right? But here is gonna be alpha. So let me draw that a bit neater. Okay, let's do it this way. All right, so here instead of carrying the weight up, we bring the reaction down, right? So here would be W instead. The reaction would come here, right? And we know this is alpha, yeah? The reaction R, this way. And then here is your force F, which acts this way, which would act this way. And we end up with our same cyclic head to tail for basic equilibrium, right? Okay, now we don't know this angle. We do know this one. So if we were to quantify this in this very unusual triangle, it's not a right angle triangle. We need more. If we just had weight and this angle, do you think there's anything we can do to solve for either R or for F? No. So we need another angle. So let's find out what this angle is, right? This angle is between R and F. So F, let's say it came here, we slid it down here, and let's put back this perpendicular line, this parallel line, sorry. So R is perpendicular to the inclined plane, and this here is parallel to the inclined plane, right? So here should be a 90-degree angle, right? And this angle here should be theta also. Yep, just simple X angle, right? Or you can go around doing this is 180, subtract here and find the angle another way. But I hope everyone can see that this angle here is also theta. Yeah. So here, this angle here is the same as this entire angle here. So let's just call this angle here, let's call it 90 plus theta, right? Because theta is some unknown angle to the plane that we're applying this force for this general case. So let's set it up. This is a non-right angle triangle, so we should use sine rule or cosine if you can, and try and solve for F. So F over sine alpha, right? Alpha is equal to W over sine W sine 90 plus theta. Solving for F, Solving for f, we end up with this, right? W sine alpha divided by sine 90 plus theta. Now, from math, we know that sine 90 plus theta is the same as cosine of theta. Yeah, this is something you should know, right? And it's just because the sine is a 90 degrees phase shift of the cosine, or the cosine is a 90 degrees phase shift of sine, right? They differ 90 degrees apart in terms of their waveform. So if we know this, we replace this with cosine theta, right? Any questions on this? No. Okay. And for this case, this is how we find f, right? So this is our third and final formula. And these are all the cases you're going to come across, right? F is equal to W sine alpha over cosine theta. And work, you might find it something like this: F cosine theta, right? Times L is equal to W by H. And as you break this down into height over length, you can see how that would come about, right? So that's the third and final case. We did number 1 already. Let's move on to number 2. A body having a mass of 20 kgs is pulled at a uniform speed of a smooth inclined plane having a gradient of 1 in 3. Calculate the force required if it acts A, parallel to the plane, or B, horizontally. So these are two use cases we already developed formulas for, right? Yeah. So parallel to the plane, let's see. Parallel to the plane, we know F is equal to W sine alpha parallel to the plane, and that sine alpha is equal to height over length. And for this problem, the length of the inclined plane is 3 and the height is 1 over 3, right? And the weight is 20 kgs times, of course, gravity, right? So we end up with F being equal to 20 times 9.81 divided by 3, and that should give us 65.4 newtons, right? Newtons. And you can double check this with your calculator. All right. So for this question, I didn't put the work in it. I didn't have time to do it. So, but the answer is here. And as you can see, using the formula, you can get the answer fairly quickly, right? This particular use case. Now, when it's parallel, when it's horizontal to the plane, horizontal, we know F is equal to W and tan of alpha, right? And tan of alpha is equal to the height over the base. The height we know is 1. The base we don't know, so let's find the base using Pythagoras Theorem. b is equal to root 3 squared minus 1 squared. 1 squared is 1, 3 squared is 9. So b is the square root of 8. And the square root of 8 is 2.3. 2.3. You can double check this with your calculator, right? So now let's add b in as 2.3. Is it 2.3 though? Nah. 2.83. 2.83. And then substituting now weight. F is equal to the 20 kgs times the 9.81, which is gravity, divided by that 2.83. So we can get the force needed horizontally to hold this, to pull this thing at a constant speed. Should be equal to 69.3, right? Yeah, this should give you 69.3. You can work this out, work along with me, get the answer. And I sent this handout already. If you didn't get it, send me an email and then I'll send it to you, right? Yeah. So that's it. And you can work this question on your own and make sure you get the same answer. Right? As long as you know the formula, again, very easy. Moving on. Number 3. A smooth inclined plane has a gradient of 1 in 6. Calculate the mass of a body that can be held in equilibrium on the plane by a force of 8 newtons when the force acts A, parallel to the plane, and B, horizontally. Again, we already solved these formulas. We already proved them. F, W sine alpha. We know the gradient, 1 in 6. So 1 in 6. Every 6 units, we move along the inclined plane. That carries us up 1 unit in height. So 1 in 6. That's what that means. Okay? 1 in 6. For every 6 units along the inclined plane, we move up 1 in height. 1 in 6. Replacing this in terms of height and length, 1 upon 6, right? But this time, they want to know what the mass of the body or how much weight we can hold with this force, with this 8 newtons force. How much weight can we hold when it's parallel and when it's horizontal? And maybe we can see which one's more, right? If we can hold more weight with it parallel or hold more weight with it horizontally. Right? So again, replacing that. Replacing F this time. F with 8 newtons we're given, and solving for W. So W is equal to 80 newtons times 6, which is equal to 480 newtons, right? And it's important to remember to not stop here, because of course this is weight and we are asked to calculate the mass, or this is downward force as a result of gravity, and we are asked to calculate the mass of a body. So we know if this is the downward force, then the mass would be this divided by gravity, because weight would be the mass times gravity. So mass should be that weight divided by gravity. Yeah, the gravitational constant. Doing that, we find the mass to be 48.93 kilograms. So we take the weight and we divide it by the gravitational constant. And of course, we get our units in kg. And we find that the mass that we can hold parallel to the inclined plane or along the inclined plane, right, is 48.93 kilograms. Right? Okay. And that's part A, parallel to the plane. Now for part B, horizontally, we solved the horizontal formula already. Tan alpha, again, W tan alpha, replace tan alpha with height base 1 upon the base, 1 upon the base. We input the F we were given, the force we were given, and we want to know how much weight, or in turn, how much mass we can hold. How heavy an object can we hold? So using Pythagoras Theorem, solving for the base, the length of the base, or B, right? So we know the length of the slope is 6 squared minus 1 squared. 6 squared is 36, minus 1, which is minus 1 squared, which is 1. That should give us 35. And the root of 35 is 5.92. We're introducing this 5.92 into our formula and solving for W. So we end up with W equal to 80 times 5.92. And that should give us 473.6 newtons. Right? 473.6 newtons. Again, solving for mass, we divide by the gravitational constant, divide by 9.81, and we end up with 48.277 kgs. Yeah, kgs.
So our mass changed, right? It changed slightly.
Yeah, what were you saying?
Sir, you notice the mass changed slightly, sir?
Yeah.
Like
so we can say
from 0.9.
Yeah.
From 0.9 to
0.2.
0.27.
Yeah. So what should that tell us? What should that tell us? That maybe pulling it parallel to the plane might be more efficient or allow us to hold more weight than pulling it horizontally. And of course, with our plane, right, we can do some other tests, run some other calculations for, practice and understanding's sake. We can do some in between and see maybe if the weight we're allowed to pull increases, right, up to the parallel, and see if it continues increasing past the parallel, yeah?
Sir, mass and weight is completely two different things, sir. So why do we get the same mass, like the exact same value, or it should vary probably slightly because of decimal place, but there's like a large difference, sir.
Okay, no. Okay, we're giving the force, right? Right? And we have to calculate the mass of a body, right? The mass here is modular. It's modular, yeah? Right? We want to find if we have this fixed force, right? And we move this fixed force from pulling parallel to pulling horizontal. Does it affect how much weight or how heavy an object we can hold or we can pull?
I understand.
Yeah. So the mass should change because the way we're applying the force is changing. The way we're applying the force is changing.
And
So
the
that's
twist
what I
constant.
said.
Yeah, I get it now.
So that's what I said. Maybe pulling parallel is more efficient than pulling horizontal. And you can do some experiments, maybe at some angle in between and some angle beyond parallel, like with theta, and see if keep moving the force this way makes it, you know, more efficient, or is it only up until we reach the parallel? So you can do some experiments like that on your own and find out which is the most efficient way to pull it, right? Up an inclined plane. Good. So we understand this, yeah? All right, moving on. And remember, the weight should change because the direction we're pulling changes. So number 4. And I want you guys to notice how quickly we can do number 4, right? Because we already have the formula. We already deduced this formula. We understand this formula. This formula is a part of us. And we understand how we get every single component of this formula. So when given the same parameters, given a question with a similar model, a similar paradigm, we can just apply this formula, right? Because we know it. A body having a mass of 5 tons is hauled at a constant speed up a smooth plane, which is inclined at 10 degrees to the horizontal. Calculate the value of the force required parallel to the plane. So when the effort is along the plane or parallel, right, parallel, we use what formula? F is equal to W sine alpha. W sine alpha, right? Now, they gave us alpha. In this case, they gave us alpha as 10 degrees, yeah? The inclined plane, which is inclined at 10 degrees to the horizontal. So they gave us alpha, which is great. We can replace this with 10 degrees, yeah? 10 degrees, yeah. And 5 tons. Well, 5 tons is 5,000 kg. So the weight would be that times 9.81, or the downward force as a result of gravity. So given that we already know the formula, and we are given so many things, we can just plot this down, boom. F is equal to W times sine alpha. We know the weight is 5,000 kg times 9.81. And we know that sine of alpha is 10 degrees. So we can solve this entire question in just one line. Or maybe 1, 2, and it's done, right? Simplifying this, plugging this into a calculator should give you 8,517 newtons, or rounding up, 8.52 kilonewtons. Yeah. Any questions? No questions? All right, so number 4, very easy. 1 lines, 2 lines max to solve number 4. Now number 5, again, I didn't put the work in it, but let me just guide you through how we would go about solving this one. An inclined plane rises 1 meter for every x meter of its length. A force of 60 newtons acting parallel to the plane is required to haul a body of weight 450 newtons at a uniform speed up the plane. Calculate the value of x, assuming friction is negligible, right? So it's smooth. So let's set up our formula. F is equal to W sine alpha, but instead we're 1 meter for the height and x meters for the length, right? This here is your sine alpha, 1 upon x. So someone plug in the value of weight, plug in the force 60, and tell me and solve this equation for x, and tell me whether or not you get a 7.5. So take a few minutes, do this, and tell me whether or not you get 7.5.
Yes, sir. 7.5.
1.5?
Yes, sir.
All right. Anyone had any problems finding 7.5 or unsure about how we get this formula? Anything like that? Okay. All right. So we could solve number 5 easily, right? Again. So we did 5 questions in under an hour. Right. So this topic should be particularly easy when it comes to doing this as a test, right? Finish in 2 minutes and you got a lot of time to check over. Make sure you didn't make any mistakes. And please guys, remember to check over, because even though these topics are easy, sometimes you might underestimate the question or write down something wrong. And sometimes you see 30 kgs, you write down 25, you write down 20. So when you finish your test, make sure you check over, yeah? Because you never know. You might just write something down wrong or plug something wrong into a calculator. So always check over. Number 6, a body having a mass of 30 kgs rests on, again, a smooth plane inclined at 20 degrees to the horizontal and held in equilibrium by a horizontal force P. Determine the magnitude of force P and the reaction between the load and the inclined plane. So let's draw an inclined plane here. An inclined plane here. Right? Okay. So some mass, some 30 kg mass. So they give us the mass and we can find that. Let's call it W. So we know W, right? And they want us to find graphically, of course, the reaction R and the force P. And the force P moves horizontally, right? Horizontally, like this. Good. So we know, creating our force triangle here, that F is equal to W tan alpha. The plane is inclined at 20 degrees, so alpha should be 20. Alpha should be 20. And the weight is 30 kgs times 9.81 times tan 20, right? Times tan 20. So work this out and tell me whether or not you get 107, and then we'll work for the force R. So P, this force P would be equal to W tan alpha, right? So work this out, let me know. Let me know if you get any issues. You should get 107.
Yes, sir. That's correct.
All right, good. So now, knowing this, right, we have W here, going there. We have P here, right, right angles. Slide P down, P. And then R is something here, right? R is something here. So we can use Pythagoras Theorem and find R, right? You guys should be able to do that, right? Found P is 107. We know W is 30 times 9.81. So R should just be equal to W squared, right? Plus P squared, right? And you can check that on your own time, right? Find R. Alternatively, you may wish to try this problem graphically, so you can always take out some graph paper, your protractor, and your ruler, and you can, you know, solve it graphically. It's not too hard to solve it graphically, you know, just plot your lines and use some kind of a scale. Maybe 1 Newton is equal to 1 centimeter or 1 square in your graph paper, right? So you can do that. And you can solve this problem, and you can use your protractor for 20 degrees, right? Right. Okay, moving on, number 7. A body having a weight of 60 newtons rests on a smooth inclined plane at 30 degrees to the horizontal. Determine A, the horizontal force required, right? Prevent the body from sliding down the plane. The value and direction of the least force required to pull the body up the plane. Up the plane, right? So when the effort is horizontal, we know our formula, right? We know our formula. Tan alpha, W times tan alpha. W, the weight, body having a weight of 60 newtons. So F is equal to 60 newtons times tan of 30 degrees. Plug that in our calculators, and it should give us 34.64 newtons. Yep, 34.64 newtons. Good. Now, next, we need to find the value and direction of the least force required to pull the body up the plane. So, when the effort is along the inclined plane, W sine alpha, alpha here is 30 degrees, yeah? And W is 60. So, finding that, again, put it into our calculator. Sine of 30 is a half, is 0.5. 0.5 times 60 should give us 30 meters. And again, since we're pulling along the inclined plane, right? Along the inclined plane, that should be direction-wise, since the plane is inclined at 30 degrees, if the plane is inclined at 30 degrees, and we're pulling along this plane here at 30 degrees, right? Then that should be the direction of this force, right? At 30 degrees to the horizontal. Yeah. And remember, do your calculations, do your experiment, and find whether pulling horizontally, pulling parallel to the plane, or pulling at some angle to the plane, which one is more efficient, right? Which one requires the least force? So do your different calculations and get back to me. But for this question, let's use when the effort is along the plane or parallel to the inclined plane, right? Yeah. So number 8, a smooth inclined plane has a gradient of 1 in 5. A body having a mass of 60 kg rests on the plane. Draw the force diagram to scale, and from the diagram, determine the effort required to pull the body at uniform speed up the plane if the effort makes an angle of 30 degrees with the plane. So we're not going to draw it to scale. You guys can do that at home if you want. But we're going to calculate it. Yeah. So this is that unusual case we did, right? So the inclined plane is 5 in 1. 5 in 1, right? the mass is of course 60 kgs. So we know that, we know the weight. But the effort required to pull the body at uniform speed, right, at uniform speed, of the plane, if the effort makes an angle, right, the effort is making an angle of 30 degrees with the plane. With the plane, the effort is making some angle theta, right, and in this case, it's 30 degrees, right? So we use this other formula that we came up with, right? This other one. Now, the angle theta, when the effort makes an angle theta with the plane, the angle theta in this case is 30 degrees. So 30 degrees here, 30. And we know sinus alpha as being the height over the length, right? Over the length, which is 1/5. So replacing that here and here, and we know weight as being 60 kg times gravitational constant. Plug all of this into our calculators, right, and see what we get. Let me just verify. 60 times 9.81, that's equal to 588.6 times 1 divided by 5, and all of that divided by cosine 30 gives us 135.93 newtons. Any questions about any of the other questions or this one? All right, so let's move on to our last and final question. Number 9. Now, as you notice, we did a lot of questions in a very short time. And that's just because we established these formulas, right? And these questions aren't particularly hard. So we can do a lot of them. All right, and I think the handout only has 11 of them. It's just number 10 and number 11 are a bit, well, they require friction, right? So we'll learn how to work those at another time. All right, so number 9. The slope of a smooth inclined plane is 20 degrees to the horizontal. A force of 400 newtons inclined at an angle of 15 degrees to the plane holds a body in equilibrium. Determine graphically or otherwise the mass of the body. So again, this formula, this methodology. Alternatively, you can work this using the principle of work. We can say the component of the force parallel to the plane is cosine theta, and it moves along the length L, and the work done on the body is W times the height lifted, which will be H. You can alternatively use this instead of this. The formula is easy, yeah? So the slope of the inclined plane is 20 degrees. So we put that in here, 20. The force, 400 newtons, inclined at an angle of 15 degrees to the plane. So here, 15. We're given F as 400. And now we want to find W, and then again, use that to find mass. So put in the values we have. Here, here, and here. And solving for W, we get W is equal to 400 times cosine of 15 divided by sine of 20. Plugging this into our calculator, we should get W is being equal to 1,129.6 newtons, right? 1,129.6 newtons. Now, again, we can't stop here because we need to determine the mass of the body, not the weight applied downwards by the body. So dividing that by the gravitational constant gives us a mass of 115 kilograms, right? 115 kilograms. And that's it. Simple. Number 9, you see. 1 line and 2 lines and 3 lines. That's it for number 9. Any questions overall on this question or any other one? No. All right, well, that's it. Hope you guys learned something. Right? I don't know whether or not you have a test this Friday. Mr. Sill did not contact me about the test, so I guess you guys won't be having a test, but just contact Mr. Sill to verify if you're unsure as to whether or not you will be having a test. All right, I sent you this handout before. Give me a few hours to upload this recording to YouTube. And yep, that's it. That's all I have for you guys. Enjoy the rest of your day.
Sir.
Yep.
Where can I find this on YouTube? Like, what do I have to search to find it?
It's didn't I send you guys a link? A YouTube link? The video?
I'm not sure.
All right, what's your name?
Troy, sir.
Troy what?
Troy Alfred.
All right, you got my emails, right?
Yes, sir.
All right, so I'll email the link. And you just click on the
Okay.
channel and you'll get all the videos will be right there, right?
Okay, no problem.
All right, anyone else?
Yes, sir. Christopher Dodger.
Yep. Send you the link also, Christopher.
Yes, sir.
Okay, all right. Good trying, Christopher. I'll send everyone. I'll send the entire group. Yeah.
Sir, could you please go over about how you derive them formula?
Which one? All of them?
Yes, sir.
All right.
I had come in late because of internet issues.
Yeah, no worries. Okay, good. So, you understand this setup, right? A body having a weight of 500 newtons, right? The weight would go downwards, inclined on a plane, right? And they give us the top of the plane, 5 and 2. Calculate the force required to hold the body in equilibrium if it is applied parallel to the plane, right? Parallel to the plane here. And of course, this is a smooth inclined plane. Smooth inclined plane. So the reaction should be perpendicular, right? Should be perpendicular. We're pulling parallel to the plane, and the reaction should be perpendicular, right? So let's create a force triangle. Okay, how we do that? Slide this up here, right? This is F, move it there, like here. And W we could put here. W we could put here. And we create this force triangle. Now, I don't know if you can see it right away, but this angle here is alpha. And this angle here is also alpha. Okay, which is this same alpha here. So we can say that here, right? Opposite hypotenuse F is equal to W sine of alpha. Are you okay with this, or do you want me to break down alpha and break down this equation more?
Oh no, I get it mixed up with his W. I thinking his W was work all the time. I
No,
understand now, sir.
W is weight. W is weight, right? So W sine alpha. And we know sine alpha is 2 upon 5, right? Opposite hypotenuse, right? For this triangle, right? So we can replace this with W 2 over 5. Right?
Yes, sir, you gotta go back. You gotta go through the rest then. And they just get mixed up with the W.
Okay, good. And you could always watch the
Understand
video
me?
and catch the piece that you didn't get, right?
Yeah, I can do that.
All right, good.
And
So that's it.
also,
That's the end of the class. That's all I have for you.